Hello and welcome to this video in the course Introduction to Data Science with R for Social Scientists. In this video, I want to walk you through the chapter 3 in the book R for Data Science, which is about data visualization. And just for the sake of this video, I will change my RStudio layout to a bit of an awkward pane layout, where we have the packages here and the help here, and I will enlarge the source pane and the packages and help pane here, and will set up my screen so that we can look at the book and the source side by side. So first of all, I will make a new R Markdown file, which I call notes on chapter 3 of the book R for Data Science, and I will delete all of the existing code from here so that we can start from a fresh document. Now that this is done, we can copy the first code chunk over from the book, which is the library command that loads the tidyverse package. And again, you have to use the keyboard shortcut Control Alt and I to make a new code chunk. You can only run code chunks in R Markdown files, so you have to insert these signs here, and of course you can type them manually, but it's much quicker to use the shortcut and then you can load the library. You can run a code chunk by pressing the little run current code chunk arrow here, or you can use the keyboard command Control and Enter. This is what I'll do here. And as you can see, the output is basically the same as what is shown here in the book. If for whatever reason you don't have the tidyverse package now, you will get an error message, and I can show this by calling on a package that doesn't exist. Let's call this does not exist. And then you will get this message here. There is no package called does not exist, which makes sense because, I mean, this actually doesn't exist. But if you get this message for a package which you actually want to load and which I showed you here, then you have to insert the command install packages. Sometimes it can happen that you have a typo here. So let's say you forgot the E. So if that happens, you will get the same error message. So always make sure you typed in the correct package name. You can also autofill the package name by pressing the tab button, and it will automatically add the rest of the package name here. Once this is loaded, I'll use a comment here. This basically means that this command won't be run, and it is indicated by R Markdown, which is changing the font color here, and we can move on to the first steps. So what the book does here is to use the dataset MPG, and I will make a new code chunk here and insert it. You don't have to load this table into RStudio. It is also automatically loaded whenever you open up R. So what you can do here is simply run this code chunk, and you will see that this is now inside of RStudio. What you can also do is to look at it in more detail by using the view command, and you can put in the name of a data set here, or any object really, and look at it using view, which is this helpful Excel-like spreadsheet viewer. And here it's easier to look at the data set. You can scroll through it, and you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 columns, and for 234 rows with data. And what this data set consists of is basically cars. You see the manufacturer here. So this is an Audi A4 with a 1.8 liter engine size, built in or fabricated in 1999. It has 4 cylinders. It has an auto transmission, and you can look up what the rest of the columns stand for by looking at the help file. And this is exactly what we will do now. We will look at the help using the question mark and then mpg. This will open up the help file here. I'm using this layout, and it basically tells you for every column what exactly it means. So if you go down here, HWY means highway miles per gallon, which is of course the American way of measuring how far a car can go with a certain amount of gasoline. So you don't want to keep these two commands inside of the code chunk because they will be evaluated whenever you knit the document to a more useful format, such as a PDF, HTML, or a Word document. So what I'm doing here is I'm copying it down here. So then you will know what you can do with the dataset, but the commands won't interfere with knitting the document. So I moved this outside of the code chunk, but left it in the script, which I will share after class with you. Now that we know a little bit more about the actual dataset that we use, we can run the first command from the book. And again, I'm adding a code chunk here, and I can also use the copy to clipboard button here, and I will copy this over and run the code chunk using the current code chunk button here. And as you can see, it will produce the exact same plot that is shown in the book. Now, the book starts by asking the question, do cars with bigger engines use more than cars with smaller engines? And as you can see in this plot, there's a negative overall relationship between the size of the engine, which is displayed in engine displacement in liters down here, with how far the car can go, which is measured again in highway miles per gallon. So how many miles can a car go using one gallon of gasoline? So this car right here, you can see it has a bit under 2 liter of engine size, and it can go over 40 miles on a highway. So using this very simple plot can already answer the question asked in the book. And this is basically how you can use those simple kinds of plots to establish a first insight into the relationship between two categories. Now, what exactly does this command do? So maybe let's start with a more simple function. As I showed last time, we can simply use hist, which is the base R command to create a histogram. We can use it here to demonstrate how an R function looks like. It starts by the command itself, then you have an open bracket. In here you will put the arguments, and we will say X, so the data set that we will use is mpg, and we want to display. Now, I don't want to dwell on the differences between the plotting system built into R and the one taught in the book, but most people believe that using the grammar of graphics, which is taught here, is superior, as you're not limited to the arguments built into a function, but you can build basically your own plots using a consistent language which is based on set grammar. The main idea behind it is that you build up a plot in different layers. So if we remove the second layer, so let's just first display this. If we remove the second layer here, which maps columns of the data set to aesthetics, so the AES command inside the geom point command maps the data to aesthetics in the plot. If we remove this and we look at it, we can see that ggplot will simply show us a blank canvas, basically. You can think of it like a painter who has just set up a blank canvas, and now he or she wants to add something to it, and in ggplot this is done by adding layers. In this case, we want to add geom, and we are adding the geom point layer here. Let's take this idea further by adding something else to the plot, and the way this is done in ggplot is by adding a plus at the end of the line. And then starting a new line with a different command, I will use the labs command, which adds labels to the plot. And I'm doing this because honestly, I find the labels in the dataset disorientingly bad. So we can change the title of the X and the Y axis here, and this is done by giving names to the aesthetics. So for the X aesthetic, which is currently called disp, I will look up what dispel means, and it's the engine displacement in liters. Instead, I will just call this engine size in liters. So when I do this, it changes the title of the x-axis. I will do the same with the y-axis. So y, and note the quotation marks here. This basically transforms this piece of text into a character vector that is used to form the label for the aesthetic. So the y, HWY, is highway miles per gallon, and I will just call this miles per gallon to make it short. As you can see, we can quickly change the style of the plot. Another thing that is really cool about ggplot is that you can change the whole theme of the plot by simply adding a different theme, and there are a couple ones built into ggplot. You can see them by typing theme and then pressing the tab button, and I choose the minimal theme in this case. Once you run this, the plot will look quite different, and I think this is just generally nicer. So here we go. This is how you slowly build up a plot, and it concludes the first subchapter here. There are also exercises which you can do, and I encourage you to do them and then send the results to me so I can look through them and see if you actually did the right thing. I will simply copy this into the file here, and I will send you the file so you can work through the exercises by answering the questions here. Moving on to the next chapter, which is about aesthetic mappings. Now, we've already seen two aesthetic mappings in the last plot here, and I'm using it as a template to continue by just copying and pasting it to this next chapter here. So the two aesthetic mappings that we've seen already are the values on the x and y axis. We map the x-axis to engine size in liters here, and the value of a point on the x-axis is shown by how far on the right it is on the x-axis here. We've mapped the y-axis to highway miles per gallon, and a point that is at the 30 line here is a car that has a value of 30 in the column highway miles per gallon. Now we can also use other aesthetics, and we can check the help file for the geoPoint function here. Scrolling down a little bit, you can see that there are a number of aesthetics that we could use. And to answer the question that is posted in this chapter here, how can we explain this car? So the ones in red here, and I don't want to show you how you can color specific points. It's a bit more advanced. We will see later on how this plot was created. But how can we explain this? We can relatively easily find out using another aesthetic. And we could try with the alpha values, so how transparent is a point in this plot, or we could directly go to the color aesthetic, which is probably the most useful here. And we can check the data set again to see what other columns we have, what other data variables we could map to the specific new aesthetic. And we could map, for example, the manufacturer here if we think that one of the manufacturers has a especially high mileage per gallon ratio. Or we could look at the model, we could look at the fabrication year, at the transmission, and so on. But we will do what the book suggests and look at the class variable here. So to map the class variable to the color aesthetics, we can simply add inside of the AES function color equals class. And using this, we can already answer the question, because the data points which have a relatively large engine size, but still a relatively large miles per gallon, so it is not following the general trend, those cars are mostly two-seaters, or more specifically, they are sports cars in this case. But we could have also tried and use one of the other aesthetics here. We could, for example, use the fill variable, and we can just try this out by mapping class to fill. But as you can see, in this case, it doesn't do anything. And the reason for that is that the specific shape that we choose, so the regular point, doesn't really do anything with a fill aesthetic. The color of it is completely determined by color. We could also use the shape. So let's plug in the shape aesthetic here. And when we do this, you will see that it is a little bit harder to see. And the reason is that we have so many different classes that the shapes get rather obscure. So this aesthetic is best used when you only have like 2 or 3 different levels of a column. And as you can see, it gets a bit more obscure, and then the SUV level is completely omitted because ggplot simply ran out of different shapes to use here. We could also use the size aesthetic, and when we plug this in here, you will see that the different classes now have different sizes. This is rather hard to spot, and as you can imagine, it is more useful if you have a continuous variable. So let's look for a continuous variable here. And you can see that besides the HWY, we also have the CTY, which is city miles per gallon. And to see if it is useful, if the aesthetic can be useful, we can simply map this variable to the size. So here we go. We can see that as the city miles per gallon increase, the points increase as well. And it is not very surprising that city miles per gallon and highway miles per gallon are almost the same. So you can see that the larger points appear higher on the y-axis. We can also use different aesthetics at the same point. So we can say color is mapped to the class, and the size stays mapped to city miles per gallon. And by combining this, we can simply use more of the columns in our data set in the same plot. And as you can see, R has helpfully added 2 legends here, which explain what the different point sizes and the different colors actually mean. Moving on to the last one, which is stroke. When I replace the color value with the stroke value here, you can see that this doesn't work, but throws an error instead. The reason is that not every aesthetic can be used with all different kinds of data, but instead for the stroke aesthetic here, you actually need a numeric variable. Let's try instead to map this to CTY, which is a numeric argument. And as you can see here, it gets a bit crazy, and I let you figure out in this help file what the stroke aesthetic specifically does. but as you can see, it somehow determines the size of the different points. Now, finding the aesthetic which can show a specific variable best needs a bit of practice, and sometimes you need to try a few different things to work, but this is basically all there is to know at the moment about the different aesthetics in R. But what I also need to mention is that geom_point not only can map aesthetics to data points, but what you can also do is to take this aesthetic outside of the AES function inside the geom_point and map it to just a single value. Let's try to make all of the points red here, for example, and we can do this. And it probably makes sense to remove the stroke because it's a little bit disorienting. But what this does is basically map all the points in our plot to a single value. We can do this if we don't really need this aesthetic, but for example, we find the default black to be not that nice, and we want to use gray instead, which maybe looks a little bit better. So when you get confused about this, the aesthetic going inside of the AES command always maps data points to an aesthetic, and then if you move this outside, it means that you use one value for all the points in your plot. And this basically already concludes this subsection, and I will leave the exercises again for you to do at home. Now, section 3.4 mentions a few common problems. For example, every open bracket in R needs to be matched by a closing bracket. So something that you will probably do early on when you start using R is that you forget one of these brackets. So say you forget this one here, and just so you've seen this once, the function won't execute, and instead you will get a helpful X here saying unmatched opening bracket. There's also a useful option for RStudio globally, which can be found in the global options and then under code in the display tab, and you can select rainbow parentheses here, and once you've selected this, the parentheses are colored, and as you can see here, this one is pink and the next one is brown. We can also take this a little bit further, and sometimes in R you will have many different brackets, but you won't get confused using these rainbow brackets because you will always see, okay, the blue one here matches the blue one over there. At some point you will probably also forget to close one of the quotation marks, and this leads to a different problem, which you can see when you execute the code and then open up the console to see, is that the console will show you these plus signs here, and it will seem that you are stuck, especially because running the whole code chunk again will now produce an error. So when something like this happens, you can press escape or Control C to stop R from executing, and you will then have to look in your code for what exactly has gone wrong. RStudio again uses colors to help you a bit here. As you can see, everything inside of quotation marks is colored in green, and you can see that labs suddenly is colored green, so you missed the closing quotation mark somewhere up here. So let's add this back in, and you can see that now the colors make sense again. A second problem that the book mentions is if you do not put the plus sign at the start, at the end of the line, but instead at the start. And what happens here is that again you get an error which might look a little bit confusing, but it simply means, all right, you made a little mistake here, put it at the end of the line, and you will get your plot to work. We covered the rest of the strategies that I mentioned in the subsection in the introduction video already, so I won't repeat them. If you are unsure, go back to that video and go to the specific section of the video that mentions help, and you will be covered, I think. Moving on to chapter 3.5, which is about facets. Facets basically mean that you split up your plot into a few different subplots, which each displays a subsection of your dataset, and make it easier to understand what is happening. The variables that you should pass to the according function, which is facet rep, should be discrete. What are discrete values here? So for example, the year is a continuous variable, or the engine size is a continuous variable, because it can basically take any value from like 1 to a few thousand if you think about a giant ship or something like that, and it can also take all of the values in between. While the class is a discrete value because it can only take certain levels. It can be a compact, it can be an SUV, but it can't be, for example, 2.5 or something between SUV and midsize. It has to be one class. That is the definition of this variable. So it is a discrete variable. And what we can do with facet rep is basically shown here. I will use again our plot that we made earlier here and copy it over to the new chapter, and I will map one of the columns to a facet. We can do this by typing facet rep, and it already suggests that I use facet rep. We use this sign to determine a formula, which isn't a very mathematical thing, but it basically is a form of notation that we use in R to say, okay, we want to map the facet to the class here, and we want to have 2 rows, or we could also say we want to have 2 columns here to do it differently from the book. And what will happen now is that ggplot splits the data set in the different classes and then creates one plot for each of the classes that we have in the data set. So we have one plot for 2-seater cars, we have one plot for compact cars, one for minivan, and so on. Now, the reason why facet rep uses a formula here is because you can use it to map 2 different variables in your dataset and split the dataset accordingly. So let's try this with the number of cylinders and the class here. And when I run this code, you won't be able to see much, and I will show you a quick trick in our Markdown to set your width first and your height of the plot to make this look a little bit better, so you can actually see what is going on here. So now we see that in this plot up here, we have compact cars with 4 cylinders, then we have mid-sized cars with 4 cylinders, and so on. If you have an extremely large data set and you expect that the relationship between the x and the y-axis is different for certain cars, so for example, when we say 8-cylinder 2-seaters might have a very different relation, and the larger the engine size, the more mileage per gallon we get suddenly. You could use this plot to find out more about the relationship for certain subsections of your data. Now, the book also mentions facet grid, and the difference here is that facet grid will for one not use the endcall argument, and the second difference is that it will produce one plot for all combinations of cylinder and class, even if it is completely empty. So for example, there are no two-seaters with 5 cylinders, so this plot is empty, and as you can guess, most often facet wrap is more useful, but if you want to try and show the complete picture, then you can try facet grid instead. Again, we have a couple of exercises here, and I will copy them into the script so you can work on them at home. Moving on to geometric objects, or geoms. As is described in the book, a geom is a geometrical object that a plot uses to represent data. And it exemplifies it by showing you these two plots. Those two plots feature the exact same data, but one of them displays every single data point, while the other one uses a statistical transformation and shows you only the trend line and the confidence intervals. Now, we can recreate the plot that shows the statistical transformation by using again our initial plot here and copying it to a new section in the R Markdown document. What we do to get the statistical transformation is simply replacing the geom point geom with the geom smooth geom. And as you can see here, all of the other things that we've already done to the plot, like changing the axis values and changing the theme, stay exactly the same. This is a great advantage of using a programming language instead of a point-and-click tool. You can just copy and paste the data and always start from where you last left off. Now, usually this is plug and play, but sometimes when you did something like mapping some of the data to a specific aesthetic, like the shape we talked about earlier, you can see that this works fine with the geom point geom, but if we change it to the geom smooth, which features the statistical transformation of showing you the trend line and the confidence intervals, you will get a warning here, and ggplot simply ignores the shape aesthetic. And please ignore the other messages here. They mostly just tell you what exactly geom smooth is doing. It's a relatively verbose function, and it tells you that the dataset you've used actually has a few cases to do this kind of statistical transformation with. What you could do, however, is to use an aesthetic that is available in the geom smooth geom, and as I've showed you before, we can simply look in the help file, and under aesthetics here we see that it has many of the same aesthetics as the geom point geom, but we use one that wasn't available before, which is the geom line one, and we can plug this in here and see how the plot changes. As you can see, similar to before in the geom point, we get a nice distinction between the different subsets of the dataset, and we can see that the straight line now represents the two-seaters. Then we have a dashed line, which are compact cars, a different form of dashes to symbolize midsize, and so on. And similar to the shape aesthetic, it gets a bit hard to distinguish once you have more than 2 or 3 different classes here. Now, there are a number of different geoms available, and one neat thing is that you can simply use several of them if you want to. So we can use the geom smooth geom, then add a plus and simply copy the first line and add the geom point here as well. I use color for both, as this makes it simpler to see what is going on. So now here we have 2 geoms on top of each other, and note that whatever you put in last, the last geom that you put in here will be on top. It doesn't make a big difference here, but if you combine several geoms, always make sure that the one you think is most important is on top, or even better, all of them are visible at once. And if you're unsure what geom makes most sense for the kind of data you have, you can open the website that is linked here and look at a few different ones. You can choose from really, at this point, hundreds of different representations of your data, as people have started to extend ggplot to and add things that are probably unavailable in all other tools to do data science and plotting. And as I said, if you want to, you can combine several of them. Now, the book also mentions another thing, which is that in this plot now we have some duplication of code. Namely, we named the mapping twice, and in this case it's exactly the same. I would always suggest to set the aesthetic mapping globally, which you can do by moving it to the first line here, to the ggplot line. And once you do this, the mapping is used for all geoms that you use in your plot. So this will produce exactly the same plot. But you can also choose to set a specific mapping here. Let's say in the geom point you want to do something a little different. So you could set either an extra aesthetic mapping here. For example, we could bring back the line type. So now the line type will only be set for the specific geom. And since I made a mistake here, you can see that ggplot gives us a warning and says this is actually not available for the geom point geom. And what I actually wanted to do is put this into the geom smooth line here. And as you can see now, the lines change for different classes of cars. As I said, I will always suggest to set a general mapping when you know this doesn't change, and only set a more specific, and only use the mapping inside the geom functions, and only set aesthetic mappings inside the geom functions if they depart from the default for the entire plot. What you can see here now is that the legend starts to look a little bit awkward. It's better than having two legends, but what ggplot does here is to combine both into one. And you can stop ggplot from displaying both legends by using the argument showLegend and setting this to false. So let's say we don't want a specific legend for the geom point geom, so we set this, and what you can see is that the little dot in the middle of the line is removed. And as the book explains, you can use the same logic to also set a data set. So here we set data equals mpg to set the data for the entire plot. But what we could also do is to use a subset of this data. And I'm just copying this from the book here because it contains a command that we will only learn later. But say we only wanted the geom smooth to show data for the class subcompact, then this is something we could accomplish like this. And what you can see here is that now everything but subcompact is removed, and the legend shows only this for our plot. This concludes chapter 3.6, and again we have a couple of exercises here that I will leave in your document for you to work on at home. So in the last section, you've already seen a statistical transformation, namely a smoother which fits a trend line to the data. And in this subsection here now, we will discuss more statistical transformations like bar charts, histograms, frequency polygons, and box plots. So what a statistical transformation does is basically perform some statistical algorithm on the data before displaying it in a plot. And for this section, we are using a new dataset called diamonds. We can, like last time, inspect the dataset using the view command. And what you can see here is that it has more than 50,000 entries, almost 54,000 entries, and 10 columns. So you see all the columns here, but you would need to scroll down a lot further before seeing all of the rows. And what we do with this new data set is to first display a geom bar, and as is explained in the book, you only map the cut column to the x-axis, and the values of the y-axis are added by ggplot directly by transforming the statistical transformation. Looking at the help function for geom bar, we can see that the algorithm used by default here is count, which means that the levels which are mapped to the x-axis will be counted, and that the fair cut level has around 2000 diamonds in it. What you also notice is that you have the stat count function documented here as well, and the reason, as explained in the book, is that it is mostly the same as geom bar, but you can choose to either run the geom function or the stat function, and they are essentially doing the same. However, what is different here is that you see that the default geom for the stat count function is the bar graph, and the default algorithm for the geom bar is the count algorithm or the count stat. Now, if you wanted to use the stat count algorithm, for example, with a different geom, what you could do here is to change the default. So say we want geom point instead. Then you can simply add this in here, and instead of bars, you get the points. The same is true for geom bar. We can use a different algorithm here. Specifically, let's calculate the density. And just like that, you have a density plot with very, very tiny bars in this case. Moving on, we can also choose to use the stat identity, and I again copy the code from the book. What's happening in this case is that we create a new small data set called demo, and we can again look at it with the view command. As you can see, it displays exactly what we defined here. So we have a cut variable and we have a frequency variable. And what this does then is that we have a data set where the variable frequency is available, and we can choose the stat identity, which simply means to display exactly what's in the data set and not to do any transformation. Now, if you paid attention while looking at the help file, you can also see that we have another function in here called geomcall, and this is shorthand for what we've done here, so creating a geom bar and then setting the stat to identity. If we replace this now and remove the identity stat, you will see that the plot looks exactly identical. This is simply done as a shorthand, since the frequency is used so often in these geom bars, and when people think of bar graphs, they often think of data sets that were already summarized to include the count or the frequency. Now, the book additionally mentions two more things that you can do with statistical transformation, namely displaying the proportion of the different cuts in here by using the stat command and wrapping it around the word prop, or using the command after stat to explain to ggplot that what we want is what is actually calculated inside of the statistical transformation function. But to be completely honest, I've never used this before. What most people usually do is to first transform the data using other tools and then using the new transformed data set inside of ggplot. This makes the statistical transformation even more transparent than what is described in the book here, because you know exactly how a certain value came to be, and additionally, you can look at the data set before plotting it, which would be a little bit difficult here since you don't see the new data set before it is plotted. And as you can see, we've reached the exercises, and again, I will copy this to the script and you can answer them inside of the R Markdown document along with your notes on the different function that I copied into here or that I wrote. Now in section 3.8 we stay with the bar charts and talk about position adjustments. What you can see here that the first two plots in the chapter map the cut variable, which indicates the quality of the cut of a diamond, to color and fill. And as we discussed before, the color aesthetic doesn't really make that much sense in a bar chart because it only displays the color on the edges, on the border of each of the bars. What makes more sense is to use the fill aesthetic, and that's what we're gonna do here by copying in this piece of code into our notes. So what this plot shows is basically the cut variable mapped to the x-axis as well as the fill argument. So we have a duplication here. Basically, we map the same variable to two different aesthetics. What usually makes more sense is to use each of the aesthetics to display a different variable, and we can do this by mapping the clarity to the fill aesthetic. Clarity is again a measurement of quality of diamonds, and when we run this code here we get a more informative plot which displays two different measurements of quality in the same plot. So on the x-axis we have again the cut variable, but now the individual segments of the plot are filled, displaying how many of the diamonds in the data set have a clarity of IF, for example. So we can see that around 1,000 diamonds have an ideal cut and an IF clarity. Now, when we look at the position argument in geom_bar, we see that the position is stacked. So the 1,000 diamonds that have an ideal cut and an IF clarity can be seen here, and then on top of this is another segment which shows the next level of clarity, which is VVS1. Now, when you compare the y-axis of this plot to this one, you can see that they are exactly the same. So this one basically also displays the count of all ideally cut diamonds, but here the individual segments of this plot are colored in. Now, as the chapter suggests, we have three alternative values for position, which is identity, dodge, and fill. So let's try these out by copying this code and pasting it at the bottom here. And first we can try the default again. To reiterate, whatever you see here is the default. So what you see in the help file is the default for an argument in your function. And when we run this, the new plot should look exactly the same, because what we've done is just make the default value explicit, but the code that runs in the background does exactly the same. And here we go, the plot looks exactly the same. Now, what happens if we change the position argument? Let's first go with identity. And on a surface level, this plot looks very similar. However, look closely at the y-axis here. So the size of this segment, which displays ideal cut and IF clarity, is exactly the same. It's around 1000. But then if you compare the second segment, which is the light green VVS1, you can see that it reaches far lower on the y-axis. In this plot here, we see it at around 3000, and here it is only slightly above the 2000 mark. And what happens here is that the yellow segment is not below the green segment here, but it is actually in front of it. So the yellow segment hides parts of the green segment, and this makes the plot a little bit harder to read and goes against much of the convention of plots, which basically means that you shouldn't use it. You can also see that L1 is completely hidden here, and this is because L1 is actually smaller than SI1. So it is completely obscured by the other segments. Now, we can make it visible again, for example, by using the alpha argument, and I'm using the same one as in the book here, which is 1/5. And as you can see, the segment becomes slightly more visible again. Compared to the last plot, all of the segments are visible, but again, it goes a bit against the convention. A reader would probably assume that we look at the stacked bar graph here, when in fact we are looking at segments which are in front of each other and obscuring each other just a bit. And I'm leaving a note here so you know that this is something that shouldn't usually be done. You can add the explanation yourself so you won't forget it when you go through the material again at some other time. Moving on, we copy the default plot again and change the position argument to fill. And note that you need to put this in quotation marks, because the value to the position argument needs to be a character vector. And what you can see here, and it's again the same plot as in the book, is that all values are now proportions of 1, which you can interpret basically as percentages. Looking again at the same segment as we did before, the yellow one here with an ideal cut and an IF clarity, we can see that it makes up, let's say around 5% of the ideally cut diamonds. This is especially useful if you want to show the distribution of different clarities in each of the different cuts. When we replace fill with dodge, you can see that now each of the segments is a bar of its own, and the bars are not as wide in this one. This makes it easier to compare the raw count, and as you can see here in the ideal cut, the clarity VS2 makes up the biggest number, which is slightly above 5000. Now, there is a final position which is mentioned in the book, and that is position jitter. We can try this out using the same plot by simply copying this code chunk and entering the position jitter. But as the book explains, this doesn't really make sense. I made it simply to demonstrate what happens when you use it on a geom bar plot. And what you can see is that the position of each of the different bars is slightly changed to the left or to the right here. What makes more sense is to go back to the MPG dataset and produce a scatter plot. So what we do here is to map displacement to the x-axis and HWY to the y-axis, and then choose position jitter. What you can see now is that many more points are visible than in the plot before, and we can quickly compare this to the normal position, which for GM point we can look up is identity. So again, when we remove this, we would get identity, but we could also make it explicit by setting the value here. And of course, you need to spell it right. And what you can see here is that a lot more points are visible using the jittering. So each of the points is moved a little bit to the left or right here. Instead of this, you can also use a specific geom, which is geom jitter, and the same as we've seen before with geom call, which is basically the same as geom bar, but with the stat identity. We can see here that geom jitter is just a geom point geom with the position set to jitter. What's important to note here is that the jittering is done randomly, so when you run this plot again, it will look a little bit different each time. So when you focus on one of the points here, you can see that it moves a little bit to the left and right, and also up and down. You can control more about the jittering by looking at the help for the function position jitter, and this essentially is the function that is called when you set the position argument to the value jitter. It puts in this function to determine the exact position of the plot, so this produces the same plot. And what you can do here specifically is, first of all, set a seed value. So basically the position of the points is still random, but it will be the same each time. So by setting a seed value in R, you can determine that the randomization algorithm starts from a specific position. So here we let it start from 1, and by setting this, it will produce the same plot each time. You can also use the width and height, which is basically determining the radius in which one of the points is displaced left or right or up and down. And let's say the y value of the points is really important. In this case, we could set the jittering of the height to 0, which basically means that it will be the exact and won't change over the iterations. And this again concludes the chapter 3.8.1. I'm leaving the exercises in the notes file here. Section 3.9 discusses coordinate systems, and I think it is easiest to explain when we look at our initial plot here again. But we move the aesthetics to the ggplot line, and we completely remove the geom. And what this leaves us with is essentially an empty canvas with just the coordinate system. The default here is a so-called Cartesian coordinate system, which basically means that the x and the y-axis act independently of each other. And as you can see, the values here symbolize something differently. So while this rather small distance on the y-axis represents an increase of 20 units on the HWY variable, roughly the same symbolizes a 2.5 increase on the x-axis. Now we can change to a different coordinate system, and something that is often useful is to flip the coordinates, which simply reverses the x and the y axis. However, we could also do the same by changing the mapping here and mapping the displacement variable to the y and the HWY to the x-axis. So this is essentially the same plot. A few others which are useful here are the coordinate with quick map. Let's first get the data for this. And what you can see is that an increase of 1 on the latitude axis is roughly the same as an increase of 1 in the longitude axis. And this is important so that maps are displayed in the correct aspect ratio. Now, the third coordinate system that is introduced here is the polar coordinates. And what the book does here is also a little bit new, because it first saves the plot in an object. The object is bar here, and when you first simply run this, you can see that it displays basically the same plot as above, just the axis is removed and the labels are removed here. And when we use the flipped coordinate system, you can see that the x and the y axis are switched. Now, when we use the polar coordinate system, we get something that remotely resembles a pie chart. Now, there's a bit of a lesson in this, because pie charts are usually not used in R, and the reason behind this is that people say, well, pie charts are actually just bar charts, which are a little bit harder to read. And this concludes the chapter. In the final subsection 3.10, we simply get a summary of all that we've learned. So we get, again, a bit of an explanation what the grammar of graphics is, namely that you can use it to describe basically any plot you want by using the simple structure. So we start with a function ggplot, we tell it what data to use, then we can add one or several geoms, we can add a coordinate system, we can add facets, we can add labels, and so on. So what ggplot basically does is to convert raw values using, for example, a stat function into a summary table, and then turns this into a nice plot. And this concludes the session. Thank you for watching the video until the end, and I hope you found it useful and will be able to finish the exercises now. You can send them to me. Please note all of the questions that you have for the first help desk session, and see you next time.